Hello everyone, and welcome to a special presentation of the launch of SpaceX's Transporter 6 mission. I am your host, Rawspace. For the next few minutes, I'll introduce you to today's mission, and one payload in particular, prior to the start of the main SpaceX broadcast, which of course you can watch right here on this stream. The Falcon 9 rocket sits fueled and ready on the launch pad at Space Launch Complex 40, Cape Canaveral, Space Force Station in Florida. There's a 90% chance of, or a 90% good on the weather, so chance of launch is very high today. This is SpaceX's first launch of 2023, but it's the 15th launch for this first stage booster. It previously launched GPS-33, TurkSat-5A, Transporter 2, Intelsat G33 and 34, and 10 Starlink missions, all of which I restreamed for you on this channel, incidentally. In-person viewers are in for a treat, because today the booster will be coming back to land on LZ-1 at Cape Canaveral. This is SpaceX's 6th transporter mission to deliver large numbers of small satellites into mostly Sun-Synchronous orbits. On board the Falcon 9 are 114 customer payloads, ranging in size from relatively small but too heavy to lift, down to picosats that can fit in the palm of your hand. Also on board are orbital transfer vehicles that contain yet more satellites to be deployed at a later time. The payload I'll be highlighting today is EOS SAT-1 from EOS Data Analytics. I've been meeting with the folks at EOS DA, learning about their satellite and their agro-focused monitoring platform. It's fascinating, the practical applications that spaceborne observations can yield. I personally have enjoyed looking at pretty images from space for forever, but the actionable data that you can get from satellite observations is both very valuable and beneficial to production efficiency, finances, as well as sustainability and just doing a better job of managing resources. So EOS Data Analytics is based in Menlo Park, California, just a few miles from offices of Google, Amazon, and the giant headquarters of Facebook, Meta. EOS DA also has multiple offices in Ukraine. The people I spoke with are in Kyiv, the capital. They are in the GMT +2 time zone, so they're 7 hours ahead of me, which made scheduling meetings a little tricky. EOS SAT qualifies as a small sat, though it weighs 178 kilograms, or 392 pounds, many times heavier than even the largest CubeSat. Unless you're a bodybuilder, you wouldn't be able to pick it up without mechanical assistance or a partner or two. Picking it up would also be foolish because satellites are very expensive. EOS SAT's compact frame is densely packed with technology: an attitude and orbit control system, ion thrusters, xenon fuel for those thrusters, power generation and storage, communications hardware, computers, and of course its reason for existence, remote sensing systems, aka cameras. EOS SAT-2 has 2 Dragon Eye cameras made by South African company Dragonfly Aerospace. It has a panchromatic resolution of 1.4 meters and a multispectral resolution of 2.8 meters. The pair of cameras allows it to image a swath of land 44 kilometers wide from an orbital altitude of 500 kilometers. It gathers data in 13 spectral bands, including RGB, 2 near-infrared channels, 3 red edge bands, water vapor, aerosol, panchromatic, and 2 shortwave infrared. What does all that mean? Well, spectral bands just means a range of light frequencies, a sliver or slice of the electromagnetic spectrum. It's all just photons: radio, infrared, visible light, ultraviolet, microwave, X-rays, gamma rays. Different frequencies of electromagnetic radiation have different properties and can tell us different things. Microwaves agitate water molecules, which let us heat food quickly. Radio waves help us communicate electronically. Visible light helps us avoid bumping into things. Red, green, and blue combined form the panchromatic band, which appears as black and white but has a higher resolution than the single spectrum bands. Near infrared has a slightly longer wavelength than visible light. It's just past the red end of the visible part of the spectrum that we can see. We can't see near infrared with our own eyes, but some animals can. It's used for night vision, thermal imaging, and your television's remote control. It also reflects more strongly off of leaves and canopy of healthy plants than does RGB light, so it lets us monitor vegetation and distinguish plants from water or dirt. Red edge is something I had never heard of before. It's a small slice of the spectrum sandwiched between the visible and the near-infrared, where the spectral reflectance of green vegetation changes rapidly. Looking at the red edge, we can detect vegetative stress earlier in the growth cycle. Crazy cool stuff. Stage 2 fuel load is complete, we just heard. Short wavelength infrared, or SWIR, is on the other side of near infrared with a slightly longer wavelength. It can see through some materials, and like fog or smoke, and it's used to monitor drainage, soil patterns, and crop growth. I had a chuckle while Googling information about spectral bands when I clicked one of the SWIR links and it took me right to EOS Data Analytics website. Water bands, or water vapor bands, are infrared bands that tell us the mean temperature of a layer of moisture in the atmosphere, so we can see what's happening with the distribution of moisture in the air. The aerosol band detects fine particles like dust or soot in the atmosphere. By combining different spectral bands and tracking over time, we can learn all sorts of things about what's happening with the plants, water, soil, and air. EOS Data Analytics has a platform, a website, that already enables users to monitor and track these things. Currently, they use data from third-party satellites, such as the US's Landsat-8 and Europe's Sentinel-2. However, the resolution isn't great, the interval between revisits of the same location is too long, clouds often obscure the view, the data is public, and it isn't possible to prioritize the imaging of specific areas. Another third-party option are commercial satellites, such as SuperDove and Pleiades Neo, but these services are expensive, their spectral bands aren't optimized for agricultural monitoring, and they have limited capacity due to a smaller swath size, just 14 kilometers for Pleiades Neo. Incidentally, 2 brand new Pleiades Neo satellites were just lost a couple of weeks ago when a Vega C rocket's second stage failed during launch. I posted a Space Week clip about it on my channel yesterday if you'd like to take a look. After this broadcast, of course. EOS SAT will solve many of these problems by providing higher resolution, the right spectral bands, bigger swath size, in-house data, and more frequent revisits, which will give the customers a finer granularity of tracking over time. And EOS SAT-1 is just the first of 7 EOS SATs that are planned to launch over the next 3 years. But more on that later. I had the opportunity to interview 2 people from EOS Data Analytics, Vladimir, a technical specialist, and Alexander, an agricultural scientist. I'll play that interview for you during the coast phase of today's launch, right after the booster landing and SECO-1, around 10 minutes after liftoff. There should be about a 40 to 50 minute coast phase during which I can play those interviews. I'll have the live SpaceX telemetry and tracking view off to the side so you can keep an eye on both at the same time. Make sure to stick around after the booster landing. The interview was great, and it will surely fill in some of the gaps in our knowledge about satellites and agricultural science. For now, listen to some tunes for a couple of minutes before SpaceX goes live. And thank you all for coming.
Space launch trajectory and countdown net. Pad is clear.
10, 9, 8.
Launch auto sequence
7,
has started.
6, 5, 4, 3, 2, 1.
Go for launch.
Vehicle is supersonic. Stage separation confirmed. Dragon, separation confirmed. Stage 1 is transonic. Landing legs have deployed. And Falcon 9 has landed.
You are looking at a live view of Falcon 9 set to lift off at 9:56 a.m. Eastern Time from Space Launch Complex 40 at Cape Canaveral Space Force Station in Florida. Happy New Year, everyone, and thank you for tuning in. I'm Shiva, and I'm a space operations engineer here at SpaceX, and I'm joining you from our headquarters in Hawthorne, California. Today, we are launching SpaceX's Transporter 6 mission, and as the name suggests, it's our 6th dedicated small sat rideshare program launch. This mission will mark our first launch of 2023 and our 200th mission of all time. Now on this flight are 114 spacecraft, including CubeSats, picosats, microsats, and orbital transfer vehicles carrying spacecraft to be deployed at a later time. We'll have a total of 82 deployment events, which will begin around the T+58 minute mark, and they'll last for approximately 30 minutes. Now we are expecting to lose ground station coverage partway through the deployment sequence, so only some of the deployments will be visible today. However, when we're back in range of those ground stations, we do expect to have telemetry and hear audio confirmation over the nets. Now, if you'd like to see a full list of today's payload deployments, head over to SpaceX.com. With liftoff just about 6 minutes and 20 seconds away from now, let's take a moment to learn more about the Falcon 9 that's on your screen. Now, to give you a sense of scale, this Falcon 9 rocket is standing about 3 meters short of the height of the Taj Mahal in India. It was named after the Millennium Falcon from Star Wars, and it gets that 9 number from the number of Merlin 1D engines that are at the base of the rocket.
Stage 1 fuel load is complete.
What you see on your screen are the 4 key parts that make up the rocket. We've got the first and second stages, the black inner stage in between them, and then at the very top, the payload fairing. The first stage is the bottom 2/3 of the vehicle. We refer to it as the booster, and it's got those 9 Merlin engines that do most of the work to get it off the ground and into the thinner parts of the Earth's atmosphere. About 2.5 minutes into the flight, the first stage will separate and make its way back to Earth for a land landing at landing zone 1, which is on your screen. If you're keeping track, today's mission marks the 15th flight for this particular booster. Now, on top of the first stage, we've got that black carbon fiber inner stage. It connects the 2 stages, houses the pneumatic pushers that allow the first and second stage to separate during flight, and also houses the Merlin vacuum engine during ascent. On top of the inner stage, we've got the second stage, which is what's carrying the 114 spacecraft and will take them to their eventual destination in orbit. Shortly after launch, be sure to watch
tanks are pressurizing for strong back retract.
Be sure to watch the velocity gauges that'll show up on your screen. You'll see how fast the first stage and second stages are going at separation, and you'll notice that the second stage continues to increase in velocity as we get to orbit. Now, the spacecraft are enclosed in the very top of the rocket in that large nose cone structure, which is called a fairing. Its job is to protect the satellites from the aerodynamic loads until we are out of the Earth's atmosphere, at which point the fairing will separate and expose them to the vacuum of space. You heard some callouts on the net there that we've begun pressurizing the tanks and begun pulling away the strongback. The strongback refers to that truss structure to the left of the vehicle, and we are just about T-4 minutes to go until launch. Currently healthy on the vehicle and the payloads. Propellant loading is almost fully complete on the first and second stages. We've completely loaded fuel on both the first and second stages and are finishing up liquid oxygen loading on both stages. We'll hear a call out around the T-3 minute mark for LOX load complete on the first stage, and a similar call out on the second stage around the T-2 minute mark. Looks like an absolutely beautiful day in Florida. Based on the weather report, we're only tracking a 10% probability of violation. So that means that we are a 90% chance of go weather. But for whatever reason, if we were not to launch today, we do have another opportunity tomorrow at the same time.
Stage 1 LOX load complete.
So with that call out, liquid oxygen loading is complete on the first stage. We'll hear a similar call out on the second stage. Now, our goal with these missions is to provide small satellite operators competitive pricing, increased flight opportunities, and flexibility. We're flying some really cool payloads on this mission, including spacecraft design to help monitor weather and environmental changes, as well as greenhouse gas emissions, spacecraft that improve communications for the Internet of Things, and those that also help measure and investigate galactic cosmic rays and solar rays. It's incredible how even the smallest satellites can make a meaningful contribution to the care of planet Earth and our efforts to visit other worlds. We are looking forward to providing a great ride to the 114 payloads on board today, just about 2 minutes from now. Next major milestone will be a call out for second stage LOX load complete. Once we hear that, we will be fully loaded on propellants for the launch attempt in about 2 minutes.
Stage 2 LOX load is complete.
So with that, we are fully loaded with about 1 million pounds of propellant on the vehicle. You'll see some clouds coming out from the vehicle. There they go. These clouds are coming from the transporter erector lines. The transporter erector provides the propellants to the vehicle. We're just clearing out the lines and the cold oxygen that is in those lines ends up coming into contact with the moist Florida air and produces literal clouds around the vehicle. Coming up, next major milestone will be Falcon 9's transition into startup. That means that the flight computers on board the first and second stage will have taken over the launch countdown, and they'll continue to have control of the vehicle through the rest of the mission. Next major milestone will be the launch director giving their final go for launch.
Go for launch.
And with that call, all systems go for launch. Let's watch as this Falcon 9 takes the Transporter 6 mission to orbit.
T-minus 30 seconds. T-minus 15. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff.
Good goals pitching downrange.
Stage 1 chamber pressure is nominal.
We're just about 40 seconds into flight. Falcon 9 clearing the tower at Space Launch Complex 40 and making its way to orbit. We are currently throttling down the Merlin 1D engines on the first stage in preparation for the point of max Q. That's the point of maximum aerodynamic pressure.
Falcon 9 is supersonic.
Maximum aerodynamic pressure is the point when the highest stresses are experienced by the vehicle during the ascent.
Max Q.
With that, we are through the highest stresses on the vehicle. Coming up, we've got several events back to back. The first of those is main engine cutoff, or MECO. There we'll shut down the 9 Merlin 1D engines in preparation for stage separation. Stage separation is where pneumatic pushers we'll separate the first and second stages. And then we'll have second engine start number 1. We just heard a call out for MVAC chill-in, so we've begun chilling in the turbopumps in preparation to start the Merlin vacuum engine on the second stage. While the second stage engine is burning, the first stage will be performing a flip maneuver, and then it will do a boost back burn. That boost back burn will ignite 3 of the Merlin 1D engines to make the first stage's way back towards land, since we are attempting a land landing today with this first stage. So again, those events back to back: MECO, stage separation, first stage flip, second engine start number 1, and then the boost back burn.
Stage 1 shutdown.
Stage separation confirmed.
MVAC ignition.
Stage 1 boost back startup.
So there is those 5 events. Awesome shots from the ground. You can see the first stage boosting away. That was on the left part of your screen, and the second stage continuing to burn. Now this burn on the first stage will last about 47 seconds. And the second stage is going to continue burning for a while. It will complete its burn until the T+8 minutes and 20 or so second mark. Shortly after the boost back burn ends, the next major milestone will be fairing separation. You'll see that on the right-hand side of your screen.
Stage 1 boost back shutdown.
So there is successful shutdown of the boost back burn. You're seeing some pulses there from the ground from our attitude control system. We use nitrogen gas as our attitude control medium, and it helps us keep pointed in the correct direction. Here you can see the bursts firing on the first stage on the left-hand side of your screen, as we are also deploying our grid
Fairing
fins.
separation confirmed.
On the right-hand side of your screen, you just saw fairing separation. We may get a view of those fairing halves. In fact, you can see it on the right-hand side of your screen, just behind the Merlin vacuum. Heading back to planet Earth, we will be attempting to recover both of these fairing halves once they land back in the water on a recovery vessel named Bob. Now, if you're just joining us, welcome. We're about 4.5 minutes into today's mission. We're in the first of 2 Merlin vacuum burns. First burn will last until about the T+8 minute and 20 second mark. Next major milestone will be the first stage's entry burn. First stage is on the left-hand side of your screen. And we're now looking at a view down the body of the first stage, past 2 of the grid fins back at planet Earth. Now we execute the entry burn in order to slow down the first stage before hitting the densest parts of the Earth's atmosphere.
Vehicles are on a nominal trajectory.
Without that burn, we'd be only using the atmosphere to slow down the Falcon 9, and that puts a lot of extra stresses on the rocket. So we ignite 3 of those Merlin 1D engines to slow down as we hit the thickest parts of the Earth's atmosphere. We had an on-time liftoff, 9:56 a.m. Eastern Time, from Cape Canaveral Space Force Station. And we're carrying the Transporter 6 mission on the second stage right now. It's SpaceX's 6th dedicated small-sat rideshare program and our first mission of 2023. We're targeting at least 3 dedicated rideshare flights to Sun-Synchronous orbit per year. And we also offer opportunities to ride to orbit on our Starlink missions, which launch about once a week. Now, these small sats can ride to space on our Falcon 9, Falcon Heavy, and the Starship vehicle in the not-too-distant future. You can see that the grid fins have deployed on the first stage. We've got 4 of these hypersonic grid fins near the top of the stage. And once we get into the thicker parts of the atmosphere, it's only the grid fins that do the steering. To make our way back to landing zone 1, you can actually see the Space Coast of Florida there on the left-hand side of the screen. Next major event Coming up in about 15 seconds, that's the first stage's entry burn, but will ignite 3 of the Merlin 1D engines.
Stage 2 FTS has safed.
Now keep an eye on the speed of the first stage in the lower left corner of your screen. You'll see that
Stage 1 entry burn startup.
drop off dramatically as the entry burn is slowing us down. Pretty quick burn. This one will last about 20 or so seconds.
Nominal trajectory.
Stage 1 entry burn shutdown.
And there is successful shutdown of those Merlin engines. Now, as we are slowing down, re-entering the Earth's atmosphere, if you're in the Florida area, you may hear some sonic booms.
Stage 1 FTS has safed.
We are attempting to recover this booster for the 15th time today, targeting this landing at landing zone 1. We've got just one more burn, which is the landing burn on the first stage. We'll ignite just a single center Merlin engine. That'll happen just before touchdown.
Stage 1 transonic.
On the right-hand side of your screen, we've got a ground view of stage 1. You can see the center engine has
Stage 1 landing
ignited.
burn.
We'll expect to see the 4
Stage
landing
2
legs
terminal
deploy
guidance.
for a soft touchdown at landing zone 1. Now, during this, we'll also hear a call out of second engine cutoff on the second stage.
Stage 1 landing leg deploy.
Seco.
Stage 1 landing confirmed.
So landing is complete. We also heard a call out there for Seco.
Nominal parking orbit.
Seco is second engine cutoff number 1. We just heard a call out as well for nominal parking orbit. And with that, we have landed the Falcon 9. It's our 161st landing of an orbital class rocket. This booster's 15th. Now coming up, our next major event will be in about 45 minutes. That is for second engine start number 2. And that'll be followed shortly by payload deploy of the first 35 payload deployment events. So we're gonna leave you with views from space, and we'll see you back shortly for second engine start number 2.
So to start off with, could you tell me your name and what your role is at EOS Data Analytics?
My name is Vladimir. I'm Chief Product Officer here at EOS Data Analytics with a pretty good background in product industry. I've been leading efforts of the team, and since about 2 years, I'm also a satellite program lead. So I've been in charge of building, launching, and adding our EOS SAT constellation to EOSDA business case.
My name is Alexander Krivoshein, and I'm a senior researcher at the R&D department of EOS Data Analytics company. My main activities are agrometeorology modeling, remote sensing crop monitoring, yield prediction, data analysis, machine learning, deep learning, and things like.
Now, EOS SAT is described as agro-focused. Could you explain what that means and how it compares to other Earth observation satellites?
The EOS SAT constellation, there are 3 basic points which makes this constellation agro-focused: the spectral, the spatial, and temporal resolutions. The spectral resolution is the same as Sentinel-2, but with a higher spectral resolution is the same as Sentinel-2, but with a higher spatial resolution. And this is the main point. The spatial resolution of new satellite is 3 meters, with the possibility of reducing up to 1.5 meters. And with such high resolution, it's accurate determination of different vegetation indices, different productivity index, a leaf area index, and many more. So, and of course, revisit time. After launch, the whole constellation, the revisit time will be 3 days, which fill all the gaps in temporal resolution. And its so high temporal resolution helps to observe crops almost continuously. The data from the new satellite can be combined with existing satellites, with Landsat, with Sentinel, to build long-term time series analysis. And so all these points make this constellation very agro-focused. And it will significantly affect of global assessment of crop state.
Interesting. So I've heard of Landsat. It's a venerable series of Earth observation satellites that have been in use for decades. What is Sentinel-2?
Prior to launch this new satellite, we used data from the Sentinel-2, Sentinel-1, Landsat, also from the nanosatellites, Aquaterra, Planet satellite, and GeoSat. So the satellites the data of these satellites we use right now.
I see. So you actually gather data from all over. The Terra and Aqua are two of my very favorite satellites. They've been producing gorgeous, beautiful images of Earth for, I don't know, more than 20 years now. So EOS SAT-1 is your first satellite, but I understand that EOS Data Analytics already provides agriculturally focused satellite monitoring services. Could you tell me about your platform and the features it offers?
If we go to slide number 2, you can see just overall information and about EOSDA. We're a US-based company with 5 offices across Ukraine, more than 200 employees. Also, we have about just under 30 professors now, which is pretty strong advantage overall in the possibility to develop different use cases based on satellite data. We have almost 1 million users, and we are processing around 15 million hectares, and every month we look and analyze almost 100 million square kilometers of satellite data. If we move to the next slide, you can see our core strategic products in our portfolio. So the biggest one is crop monitoring, which is obviously intended to resolve different cases in agricultural verticals, like change detection monitoring, monitor field activity, crop rotation, etc. Lots of interesting features. We also have custom solutions, is where that our science teams, our PhDs, develop different algorithms that are trained by neural networks. Features like crop classification, yield prediction, etc., also available for our customers. If we move on to the next slide, you can also see our forestry product. Basically, it's a relatively new product where we tackle the issues of forest health, illegal deforestation, and harvesting, and manage different supply chain risks related to forestry. And also we have like all-purpose GIS online analytical tool called LandViewer, where any GIS specialist can do any kind of satellite data analytics on the fly, not having to install a desktop application, but calculating everything online and on the fly.
And could you remind me what GIS stands for?
Geospatial Information Systems, if I'm not mistaken.
Now, what benefit will come from having your own satellite constellation as opposed to just using the existing data from satellites that are already up there?
Thanks. That's actually a very interesting question. That's the one we looked at even before initiating the project of launching EOS SAT. You can see there are certain risks of actually not having your own satellites and using other commercial satellite data. So number one is like majority of the companies in the market using free satellite data sources like ESA's Sentinel-2, but there we face a problem with the resolution. It's only 10-meter resolution, where in our case we have 1.5 and 3 meters. Also, there is an inherent risk that Sentinel-2 can go out of service, and I mean Sentinel-2 contains pretty strong percentage of data that we use for analytics, so that's another risk there. Also, when working with some other commercial satellite data with like comparable resolution of 3 meters, we faced a lot of issues about the data quality there. Also, again, if you buy the satellite data from someone else, logically, there will be some margin there, so your cost will be actually higher than having your own satellite. And also, another problem which we faced with the commercial data out there is not enough bands and limited possibility for analytical use cases. So by understanding all of these challenges that allowed us to realize the necessity for building our own constellation with the proper data quality, proper resolution, and proper amount of bands to leverage our analytical capabilities.
I see. And how many satellites are planned for your constellation, and what's the reasoning for that number?
We do plan to launch 7 satellites in total. I mean, if you look at the slide 6, you can see that the next satellites will be launched in the batches of 3. So 3 satellites in 2024, 3 more satellites in 2025. The main kind of strategic reason to launch 7 satellites was to achieve good revisit time globally. So we are intending to, of course, work with some big clients where they want to get exclusivity or certain areas like Australia, so we can give priority to them. But overall, we do plan to launch to monitor all agricultural and forestry lands worldwide. And in order to do that with a 5-day revisit time, we need 7 satellites. So we did some simulations and estimates on how much satellites we need, and that's how we come to understand that the 7 satellites is a perfect number in our case.
And what sort of customers use EOS Data Analytics? Like how big, how small?
That's a great question. So our clients, despite resolving mostly agricultural challenges, actually come from quite different verticals. We work with not only farmers, but also input suppliers, insurance providers, bankers. Also, we have some pretty big projects with NGOs. As I mentioned before, GIS specialists is a pretty common customer and user of our software products. For the customer size, we're obviously focusing on pretty big clients. I mean, strategic partners who are interested in our EOS SAT data, but obviously we have pretty big overall traffic to our products. So we also do have some amount of smaller clients like farmers, let's say, with 1,000 or a couple thousand hectares. But the focus on the big ones, I would say, over 50K hectares.
As far as the technical capabilities of the EOS SAT, what's it capable of? And are there any design components in particular that you can highlight?
Right. So if we go to the slide number 8, you can see overall solution and with the main technical parameters that we're going to offer with our EOS SAT constellation. So it's 1-day revisit time on specific tasking areas of interest of our clients. The resolution is panchromatic 1.5 and multispectral 3 meters. We're going to offer some exclusive products and exclusive, let's say, data contracts for specific areas to some of our big clients. As I mentioned, we're going to be focusing on covering 100% of all croplands and forest lands worldwide. Overall revisit time is going to be 5-6 days, so similar to Sentinel-2. And obviously, we're going to allow our clients to do some long-term solutions based on historical data that we are going to acquire. If we talk about overall how satellite was assembled and some design challenges the team was working on, so we can go to the slide number 9. You can see some images here of how the satellite was assembled. I mean, I want to give a big shout out to Dragonfly Aerospace, our sister company, who has built this satellite for us. I would say the biggest kind of state of the art or part of the satellite that we are really proud of is optical payload. It really has some very, very nice characteristics in terms of geospatial resolution, GSD, also amount of bands, the quality of the data, and optical payload as a kind of unique solution that we were able to achieve. And the expertise of the Dragonfly Aerospace team did help us and allowed to overcome some of the challenges and to make it happen for us.
I see. You mentioned Dragonfly Aerospace. Where are they located?
So the Dragonfly Aerospace is located in South Africa and Ukraine. So actually, the satellite was built by experienced teams of engineers in South Africa and Ukraine, also with the support of Flight Control, another our sister company. So the guys did a really good job, and they were really able to leverage their strong background and experience of building different satellites before.
So what scientific methods of data monitoring have your team applied to the EOS SAT?
We use satellite data in two ways. First is directly, just manipulate with spectral bands in order to create different vegetation indices. And second way, indirectly, by use satellite data in different process-based models and in statistical model, in machine learning methods. So, for example, we can use leaf area index in biophysical modeling, and in this way increase the biomass estimation. Or also we can use satellite data as predictors in different machine learning methods and increase the accuracy of crop classification and yield prediction. So this is the way we use the satellite data as a rule.
And what frequencies or wavelengths does EOS SAT detect?
Spectral resolution is the same as Sentinel-2 with 13 bands in visible, near-infrared, and shortwave infrared part of the spectrum. So reflectances within this range, the EOS SAT can detect.
And so what do the different wavelengths of light tell us about the land, the water, and the air? For example, what does infrared or ultraviolet tell us that visible light does not?
Based on this wide spectral, for example, there are two channels, red and blue, which can be used for retrieval of aerosol and water content in atmosphere. And this data can be used for atmospheric correction, for example. But the spectral channels separately does not tell us very much. So we usually use the combination of spectral bands. So the combination helps to highlight the specific information from the satellite image. For example, if we want to distinguish water and cropland, we can use the near-infrared and red channel, and in this way build normalized different vegetation index and extract the crop canopy and observe the crop state. Or if we need to detect, for example, water stress, we can use shortwave infrared with near-infrared channels. By manipulating with these channels, we create and developing different vegetation indices.
And so a vegetation index is some sort of insight into what's going on with the vegetation in a particular way, like what does reflectance tell you, or can you detect photosynthesis, things like that?
Yes, but basically we use these indices along with biophysical modeling, because sometimes the indices show a really huge biomass, but in real, the actual yield is pretty small. And this is the situation where the biophysical model really can help, because they can track the agrometeorological condition throughout the whole vegetation period and can detect in some development stages if crop have been under some water stress or maybe under some heat stress, and detect this as a, for example, as a stage of grain filling. And sometimes it happens that the satellite indices show the high value, but the harvest index is small, the ratio between total above ground biomass and storage organs. And that's why we use the satellite data along with biophysical modeling to detect different anomalies in the field.
Now, what kind of orbit is EOS SAT going to fly in? And can you explain why that orbit was chosen?
Yeah, absolutely. for this one, I think it makes sense to look at slide number 10. It has some pretty nice visuals on the types of orbits that satellites can fly. So we are going to use Sun-Synchronous orbit with a 9:55 a.m. Local time of ascending node. So basically, we have chosen Sun-Synchronous orbit. It was the only choice for us because it's really critical for us that all imagery taken from the satellite is taken at the same time of local time or where the satellite is flying. So we did that to make sure that the illumination characteristics are the same in all images that we're going to acquire. And it's important to make sure we can, those images are kind of comparable. So each image is taken at like 9:55 local time in the morning. And we can build long-term analytics based on our data because we kind of maintain that local time of acquiring the imagery.
So in the Sun-Synchronous orbit, the photos are all taken at the same time per day, like, as you say, 9:55 a.m.
Yeah, actually, there is some like plus minus, I would say 15-minute deviation is acceptable in terms of illumination characteristics and comparability of the imagery. But yeah, we will be aiming to acquire all the images around 10 a.m. local time to make sure it's kind of the best illumination characteristics and that our scientists are happy with how this data, how vegetation parameters can be retrieved from this data. So yeah, it's pretty important for our business case to maintain that same local time when acquiring imagery.
Is that local time, is that based on UTC, or does that vary based on like daylight savings, or is it just using the GMT offset?
So actually, that's an interesting question. The trajectory of the satellite will be kind of moving in the sync with the rotation of Earth around its axis, around the center. So the trajectory of the satellite is kind of orbital math. It's pretty complicated stuff, but we chose the inclination angle and the trajectory in a way that kind of our orbit allows satellite to be always over 10 a.m. over the point where it's kind of flying at this moment. It's kind of chasing the spin of the Earth rotation against its axis. So I don't know if it was complicated, but anyway, that's the idea that the satellite is always over the Earth at 10 a.m. whatever point of the trajectory of its orbit it's in at this moment. It's always 10 a.m. If we start acquiring the imagery kind of below the satellite.
I imagine that that's kind of like the best time to look at the moon is not during a full moon, because then the sun is straight overhead and you're not getting any shadows, so you can't see any differentiation. It's probably why you want the satellite to take a picture when the sun is at a slight angle.
Yeah,
and
because at 12 a.m. you will be getting 100% reflection of the sun. It's not the perfect. It should be any time, but not the noon.
Will the other satellites in your constellation fly at different altitudes or inclinations, or will they all fly essentially in the same orbit but just spread out across different longitudes, sort of like the stripes on the basketball?
So I think your analogy with the stripes and the basketball is pretty close. But our actual main goal of our constellation and to maintain each satellite in that same local time, or L10, local time of ascending node. So we did account for some orbital maneuvers to change the altitude mainly, but inclination a little bit as well, just so that the satellite is maintained within one local time or ascending node. So yeah, actually all the satellites will be like evenly distributed among longitudes and be flying one after another to make sure that all imagery taken by the constellation is with the same or very similar local time ascending node.
Sounds like some complicated math.
Yeah, I mean, orbital geometry is very tough. I mean, I have a math background, pretty strong one, but when I'm talking with some of the engineers from Dragonfly Aerospace, it's kind of, I have barely enough knowledge just to understand, I mean, the overall concept, what they're talking about, but not the details.
And once the constellation's fully deployed, what will be the interval or what did you call it, repeat time for passes over a particular location on the ground? Like, will it be every day or every so many days?
Right. So for each satellite in our constellation, we plan to have around like 20 overpasses per satellite per day on average. So basically, each satellite will be able to download imagery every 70 minutes or so. And I mean, for our partner in the ground station network gives us some like some 4 and 5 locations where we can downlink. And overall, we expect that it will take from like 2 hours to maybe around 16 hours between the acquisition of satellite imagery in space and making this imagery available for our end users.
And what's the planned lifetime for each EOS SAT? Are there plans to replenish the fleet or expand it in the future?
This is an interesting question. If we look at the slide 11, you can see that the design lifetime is 5-7 years. So what basically means that like official timeline of a lifetime of the satellite is 5 years, but we have accounted for some fuel reserve to allow some maneuvers for like more time. Actually, if we are lucky, we can even extend the lifetime to maybe even 10 years, but I mean 7-8 years is definitely possible. And yeah, as a baseline plan, we do have planned replacements. So as soon as the satellites go out of service, we're gonna launch new ones to replace and keep up that magical number of 7 satellites in orbit to allow us to get good revisit worldwide.
And does EOS SAT have to aim itself in different directions like a space telescope, or does it point straight down and collect data basically in a long stripe?
So actually, EOS SAT-1 and the following EOS SAT have a camera roll angle of 40 plus minus 45 degrees. So actually, it can roll to the side and acquire imagery. So not necessarily always in a long strip, but in practical terms, will most likely capture like nadir, I mean 90 degrees, or will have some relatively small use of camera roll, maybe up to 20 degrees, to make sure we're able to capture necessary areas as effectively as possible. The problem with the bigger angles, maybe if you try to take imagery like 30 degrees or maybe 40, the problem with that is that the resulting imagery will have very different reflections, parameters and characteristics, and that would degrade this imagery and make it impossible to use by our science teams. So this imagery will be incomparable with some of other imagery acquired under normal angle. So actually, we mainly will be capturing nadir and plus minus 20 degrees of camera roll.
So does EOS SAT have thrusters or gyros or flywheels? What kind of thruster technology and fuel does it use?
The different systems that you mentioned are usually part of altitude orientation and control system of the satellite. So this subsystem is basically responsible for precisely understanding where the satellite is, controlling its current position, planning for a future positioning and maneuvers, things like that. So in our case, we have things like magnetometer, star tracker, etc., to identify satellites' exact current position, and we have things like reaction wheels and propulsion to manage satellite positioning along 3-axis and manage its further trajectory and plan some maneuvers for the satellite. Again, our propulsion is quite standard, I would say, for small sats. It consists of 2 parts: it's fuel tank and thruster, and we use xenon electric propulsion for our thrusters.
I see. So ion thrusters using xenon.
Right.
Can EOS SAT's thrusters be used to dodge space debris? I know there was an incident with the ISS recently where they did have to dodge a piece of debris.
Oh, absolutely. Actually, the topic of like collision avoidance and managing risk of colliding with some other object in space is becoming more and more important during last years. Because right now in low Earth orbit there are like 4,000 to 5,000 satellites. Some of them are managed. They have propulsion left. Some of them are old satellites, but still they orbit in that low Earth orbit. We intend to leverage our propulsion system and the mission planning system to do some collision detection and plan some collision avoidance maneuvers. This topic is also affecting what kind of conditions you can get from insurers. So if you can like show you have a proper collision avoidance strategy and capability, you may get better prices for insurers to kind of have your in-orbit insurance at more affordable price. So the topic is important and becoming more and more important every year because the number of satellites being launched is just growing exponentially.
It sure is. And how will you receive the satellite data? Will your constellation be in constant contact, or will the satellites downlink their data when they fly over certain ground stations?
We'll downlink satellite data with our top-notch ground station provider from Northern Europe. We'll have contacts with the satellite whenever it's in the line of sight of the ground station or over this ground station network. And these contacts will be used to receive telemetry data from satellites and send some tasks from the satellite and to get the imagery to the ground. But overall, I mean, we won't have constant contact, but we'll have frequent contact, like every 70 minutes or something, sometimes even with a higher frequency.
And why was Falcon 9 chosen to launch EOS SAT-1? And will all of your satellites use SpaceX, or are there other launch providers being considered for the future?
So for EOS SAT-1, we have considered, I mean, 4, probably 5 launch vehicle service providers before actually choosing SpaceX. I mean, when choosing, we consider different factors. I mean, you name it: price, planned orbit. A launch success rate is also important because it affects price of launch insurance. So overall, when considering all these components, especially I would say launch success rate, SpaceX was chosen as a service provider for the launch of the EOS SAT-1 for future. I mean, we don't know yet. We are going to look at the evolving players in the market. And obviously, as we mentioned before, it's important that if we go with the SpaceX, that they can offer orbit that we need and the local time that we need. So that is also an important factor. But yeah, I mean, we'll definitely watch this launch vehicle market develop and evaluate our options going forward.
And finally, how can EOS SAT help to fight climate change and empower the sustainable use of resources?
EOS SAT constellation will help to solve different problems concerning to CO2 decreasing. Of course, directly data cannot be used for monitoring of CO2 emissions, but using this data, we can accurately estimate CO2 soil sequestration, depending on farmers' management. And that reduces the CO2 concentration and indirectly help to solve the problem of climate change. And of course, some problem according to food security, the assessment of flooded territories, ice cap melt detection. All this issue can be solved with a higher accuracy based on the new high spatial resolution data from the new satellite. And of course, as I already mentioned before, the new data from new satellite can be combined with existing ones and to build long-term time series. And based on this long-term time series, we can analyze it and estimate the potential of some territory and to provide some recommendation to farmers if this territory will, for example, if this territory can produce 2 harvests per year or not. All this can be accomplished with new satellite data. This data can be used in machine learning methods, different, and we can predict the crop yield in advance. And this is allowed to farmers to have some time to prevent measures to avoid the food demand crisis.
Excellent. Well, thank you so much for your time.
Thank you, Matt.
Thanks, Matt. It was a pleasure.
come soon. We cannot solve our problems with the same thinking we used when we created them.
Acquisition of signal, brief. Acquisition of signal, Maltese.
Welcome back to our coverage of the Transporter 6 mission. We've had a great mission so far. We lifted off on time at 9:56 a.m. Eastern, recovered our first stage at landing zone 1, and completed the first of 2 second stage burns. Now we're coming up about 20 seconds away from a quick reignition of our Merlin vacuum engine. This burn will just be 2 seconds to circularize our orbit. So coming up, second engine start number 2. And there is successful startup, SES-2, as well as second engine cutoff number 2.
Nominal orbit insertion.
With that call out from mission control, we are in the expected orbit. Now, as I just mentioned, you are watching the Transporter 6 mission. This is our 6th dedicated rideshare mission and SpaceX's first mission of 2023. The Falcon 9 lifted off at 9:56 a.m. Eastern Time from Cape Canaveral Space Force Station. in Florida. We successfully separated the stages, landed that first stage at Landing Zone 1 for our 161st recovery of an orbital class rocket, and we just completed the second of our 2 planned second stage burns. If you're not familiar with our transporter missions, they are dedicated rideshare flights. SpaceX is targeting at least 3 Sun-Synchronous orbit missions per year, in addition to various opportunities for a ride on our Starlink missions, which launch about once a week. The small sats can ride to space on our Falcon 9, Falcon Heavy, and in the not-too-distant future, Starship. Now, we've got 114 spacecraft, including CubeSats, PicoSats, microsats, and orbital transfer vehicles carrying spacecraft to be deployed at a later time in the mission. And as I mentioned earlier in the webcast, we are flying some payloads that are really cool to help monitor weather, environmental changes, greenhouse gases, satellites that improve communication for the Internet of Things, and satellites that will measure and investigate galactic cosmic rays and solar rays. Now, for the 114 spacecraft, there will be a total of 82 deployment events. Those will happen just past the T+58 minute mark, so just about a minute from now. And the payload deployments will last approximately 30 minutes. Now, unfortunately, we only have partial ground station coverage for the deployment sequence, and the ground stations are how we get our telemetry and these live views of the second stage. So we won't have coverage of all of the deployments visible today. But once we get ground station coverage back on the other side of that blackout, we'll expect to have telemetry and hear audio confirmation of the payload deploys that'll occur during that period. It's also worth mentioning that because these spacecraft are being deployed in groups in quick succession, we may not be able to confirm every deployment in real time. While you will hear most of the callouts by our mission control operators, we will try to provide updates for any that we don't hear real time by the end of the webcast. We do have a full list of the payloads on SpaceX.com if you'd like to follow along, but for now, we're going to listen in as the payload deployment sequence is about to begin.
EOS SAT-1, separation confirmed. SAT-2, separation confirmed. Lemur 2, immaculate, separation confirmed. Lemur 2, Fuententaja 01, separation confirmed. Connected T1.2, separation confirmed. Gamma Alpha, separation confirmed. Bro 8, separation confirmed. Newt, separation confirmed. Huygens, separation confirmed. Lemur 2, disclaimer, separation confirmed. Starvibe, separation confirmed.
Lemur 2, Steve Albers, separation confirmed. ISI launch Cleos KS F3A, separation confirmed. Birkeland, separation confirmed. Space B 156, 167, separation confirmed.
Expected loss of signal, reef.
Lemur 2 M Molo, separation confirmed. ISI launch Cleos KS F3B, separation confirmed. ISI launch Cleos KS F3C, separation confirmed. Lemur 2 Filari, separation confirmed. ISI launch Cleos KS F3D, separation confirmed. Flock 4Y, separation confirmed.
Qualities, expected loss of signal.
Space BD ISI launch Poly 10 from Kyiv, separation confirmed. Flock 4Y, separation confirmed. Guardian Alpha, separation confirmed. Flock 4Y, separation confirmed. Flock 4Y, separation confirmed. Space BD Sony Sphere 1, separation confirmed. ISI launch, Clyde Space, NSL SAT-2, separation confirmed. ISI launch, Sternula 1, separation confirmed. Flock 4Y, separation confirmed. Flock 4Y, separation confirmed. Flock 4Y, separation confirmed. Block 4Y, separation confirmed.
Now at this time, we've had confirmation of 33 out of the 35 deployments, but because the spacecraft on this mission are small sats, it can be sometimes difficult for us to confirm the deployments in real time. So we're going to confirm with our teams and provide an update a bit later on in the broadcast. Now, I mentioned it earlier, but we are entering into a telemetry blackout period. During this time, we're expecting to deploy an additional 20 payloads. This loss of signal will last until about the T+1 hour and 16-minute mark, so we'll be back just before then to get confirmation of the payload deployments that occur during the telemetry outage, as well as we'll be standing by for those final 27 deployments while we have telemetry back. For now, we're going to leave you with some space tunes, and we'll see you back around T+1 hour and 15 minutes.
Expected loss of signal, Bangalore.
Because these spacecraft are being deployed in groups in quick succession, we may not be able to confirm every deployment in real time, so we'll expect we may need a few extra minutes to confirm these final deployments. Let's listen in.
Acquisition of signals forward.
Separation of 20 payloads confirmed. Flock 4Y, separation 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 confirmed.
Link Tower 3, separation confirmed. Albania 1, separation confirmed. Link Tower 4, separation confirmed. YAM 5, separation confirmed.
Acquisition of signal, Pogo.
EOS SAT-34, separation confirmed. Albania 2, separation confirmed. First ISI satellite, separation confirmed. Umbra, separation confirmed. Umbra, separation confirmed. SAT-35, separation confirmed. Ion SCV-007, Glorious Gratia, separation confirmed. Ion SCV-008, Pierce Franciscus, separation confirmed. Launcher, orbiter SN1, space tug, separation confirmed. Second ISI satellite, separation confirmed. Skycraft, separation confirmed.
Expected loss of signal, small word.
Figurehead 5, separation confirmed. Chimera Leo 1, separation confirmed.
Acquisition of signal, boss.
Dragonfly Aerospace, EOS SAT-1, separation confirmed.
As you may have noticed, we were able to confirm 77 of the 82 deployments. Now, because the spacecraft on this mission are small sats and because some of them deploy in close proximity to another, it can be difficult for us to confirm the deployments in real time. I've heard from our teams that we likely won't be able to make confirmations in the next few minutes, so we're going to end our live broadcast here, but we'll provide an update on those final confirmations via our social media platforms as soon as we receive them. We want to thank you for watching today's launch, and we'll see you next time.
Thank you.